In this session, we're going to discuss projection data. We're going to start with a discussion of 2D imaging and evolve that discussion right through to three-dimensional imaging, that is CT. Here we can see a conventional plain film radiography configuration where we have a source of X-rays incident on an object and a detector. The X-rays are shown as the green lines, the object is orange as a rectangle there, and the detector is the blue rectangle. Now the interaction of each individual X-ray is probabilistic. That is, the photon can be Rayleigh scattered, Compton scattered, or photoelectrically absorbed. Here we can see an X-ray that has left the source and been photoelectrically absorbed in the object. Here we can see another X-ray that has passed through the object and been photoelectrically absorbed in the detector. And here we can see a third X-ray that has scattered in the object and then been photoelectrically absorbed in the detector. Now, when we consider each of these individual X-rays, we have to consider the attenuation of the object. Here, the attenuation of the object is expressed as a linear attenuation coefficient, and that's the Greek symbol mu. And we can see that there are brackets after the symbol mu, and inside the brackets there's a z, a rho, and an e. Now that means mu is a function and has a functional dependence on each of those three parameters. Now we're only going to consider z and rho in this section. So that is, we're going to assume that all of the incident X-rays are all the same energy, so they're monoenergetic or monochromatic. So I can reduce the number of X-rays that pass through the object and become incident on the detector by increasing the density of the object. Also, I can increase the thickness of the object. So here we see both mu and t affect the attenuation of the object. So what we actually need to consider is the product of mu and t. That's mu multiplied by t. And the product mu t is called the total attenuation, or normally just the attenuation. Normally we refer to the total attenuation as just the attenuation, but we're explicit when we discuss the linear attenuation coefficient mu. So that will be referred to as the linear attenuation coefficient, or LAC. Now we can see that the relationship between the intensity of X-rays, that's I, the intensity, coming from the source, incident on the object, and then passing through the object to be incident on the detector, that intensity I, the incident intensity I0 or I0, is diminished, and we have a lower intensity that comes out the other side of the object and can be incident on the detector. So I and I0 are related by the Beer-Lambert law. I equals I0 times e to the minus mu t. And we have the attenuation product mu t inside the brackets there. And there's a minus sign there inside the brackets. And that means that the incident intensity is going to reduce as it passes through the object. Now we know that the characteristics of an exponential decay mean that we can define a parameter by which every time we have a multiple of the thickness, the intensity will drop by half, or 50% of the incident intensity. And that parameter is called the half-value thickness. And in radiography, the half-value thickness is used to characterize the quality of the X-ray beam. So by rearranging the Beer-Lambert law and setting I on I0 equal to 0.5, we end up with the half-value thickness is the natural log of 2 divided by mu. Now in this example, the material I've chosen to plot has a half-value thickness of about 0.7 millimeters. So we can see that when I put 0.7 millimeters of thickness of material between the incident X-ray source and the detector, I0 diminishes by half, so 50% of the incident X-rays come out the other side of the material. If I put another 0.7 millimeters, that's then going to drop by half again. So now I have 1.4 millimeters of material, and my incident intensity has dropped to a quarter by the time it comes out the other side of the object. So that is I, my transmitted intensity, is a quarter of the incident intensity. Now, intensity and attenuation are inversely related. So when intensity goes down, attenuation goes up, and vice versa. So here we can see another toy scenario where we have a disc of metal. That's that blue circle, or the blue disc on the right-hand side of the slide. And we have some X-rays incident on the disc in a thin pencil beam. So that pencil beam of X-rays is tracing along that red line, and when it goes through the thickest part of the diameter of the disc, the intensity that comes out the other side of the disc is going to be at its minimum, at its lowest. And similarly, the attenuation is going to be at its highest. We are maximally attenuating the X-rays. Now, the total attenuation, which is plotted on the right-hand side there, because this is a single object made of the same material, mu is the same everywhere, so that means the product mu t, as a function of position across the object, just traces out effectively the diameter of the disc. So the attenuation is maximum when the X-rays go through the middle of the disc, and minimum when the X-rays just clip the edge of the disc. Now, the intensity profile is a little bit more complicated than that. It has a slightly different dependence, and that in order to understand that dependence, you would have to plot the intensity profile for different materials. So we can see for this very dense material, only a very, very small amount of material is needed to dramatically reduce the intensity of the X-rays from I0 to those coming out the other side of the object. So almost no X-rays are coming through the object, even when we're just clipping the edge of the object, and that's because it's a very dense material. If we used a less dense material, the intensity profile wouldn't have that harsh box-like edge and would be more rounded at the edges, as more X-rays would go through the edges compared to the centre of the material. So now we have to move on to consider what happens for multiple materials. So here to start with, we can see X-rays traversing along that pink line. We have sent 100 photons in, and 55 are coming out the other side of the blue object. So we can put the numbers into the equation here, the rearrangement of the Beer-Lambert law, and we know everything on the left-hand side. We don't know what's on the right-hand side. We have one known, one unknown. We know what's on the left. We don't know what's on the right. So we can solve the equation for the attenuation. Now, if we go to a slightly more complicated situation where we have a 2x2 grid of materials, so we have a blue material, a yellow material, a green material, and a red material, each of which have different linear attenuation coefficients. Now, the linear attenuation coefficients are additive, so we can see we have the natural log of the ratio of the intensities is equal to mu blue T blue plus mu yellow T yellow. There's a plus sign there, they're additive. But now we have we know what's on the left-hand side, but we have two unknowns on the right-hand side. We don't know the product mu T of the blue material or the product mu T of the yellow material. So because we have two unknowns, and it means we can't actually solve this equation. Now, that then is why in conventional projection imaging, all of our materials sit on top of each other. This is just the mathematical grounding for why, when we just take a single measurement along a single ray path, all of the materials that those X-rays meet and traverse, all of that information is encoded as one number in the X-ray image. If we want to disentangle that, we have to make multiple measurements, and that's why we move to CT. So if we want to do three-dimensional imaging, we have to take lots more measurements in order to solve for all these unknowns. So here we can see three simultaneous equations. I've taken my X-ray source and rotated it to three different positions around the object. The first position, the X-rays go through the blue and the yellow objects. The second position, they go through the blue and the green objects. And the third position, they go through the blue and the red objects. Now, I only had enough room to fit three forms of the equation on the slide here. Now we have four unknowns, the blue, the yellow, the green and the red, so we actually need to make a fourth measurement in order to be able to start to solve these equations and therefore regain our volumetric data. And that's what we will discuss later in terms of reconstruction. So CT is different to plain film radiography in that in order to recover the volumetric data, we take multiple measurements and then have to go through a reconstruction process. So in terms of considering the number of measurements we actually have to take, well, the number of measurements is going to depend on how many little squares we want to divide the internal anatomy of the person into. And in order to get some decent resolution, we typically need 512 by 512 squares to form one slice image in a CT reconstruction. So that means we need to take an awful lot of measurements in order to be able to solve all those equations, in order to be able to determine the picture of what is inside the patient. As you are probably aware, we do that by taking the source and the detector and rotating them around the patient. So here we can see the X-rays emanating from the green X-ray source on the slide here. They pass through the patient, which is just a head scan in this configuration, and onto the detector. So the detector banks are the red detector channels there. And each of those detector channels is making an independent measurement of the X-rays that pass through the patient. So just to reiterate, the geometry is different. So in a standard plain film radiograph, the X-rays shine through the patient. So here we can consider just a standard AP projection image. The X-rays go through the anterior, through the posterior, and onto the detector plate behind. In the CT configuration, the image is orthogonal to that. So the 512 by 512 image would be going into the slide in this configuration. Now, in order to explain some of the finer points of the attenuation profile, I've made a toy system here which consists of a black disc, which is essentially just air, and then 4 attenuating structures of different sizes. They've all got the same attenuation coefficient, so you can consider them as 4 different sized chunks of bone: a line, a circle or a disc, a square, and a point. Now, we shine the X-rays at some projection angle, so the source and the detector rotate to some projection angle, and we shine the X-rays through the patient and onto the detector pixels. And as I said before, each of those detector pixels is going to measure an intensity, and that intensity, we apply the Beer-Lambert law to convert that into an attenuation. And as we said before, attenuation and intensity are inversely related. So when I have a large amount of white object stopping the X-rays, I'm going to get a small intensity. Only a small number of X-rays are going to go through that and get to the detector pixels. But when I apply the Beer-Lambert law, that turns that into a big number. So here in the top right-hand corner, we can see a blue line which is tracing the attenuation profile that the detector pixels would measure as the X-rays pass through that object. Then I could rotate to another projection angle and take another set of measurements, take another attenuation data set, and I would get a different profile because the X-rays would see a different view through the patient. So effectively, along each one of those X-ray paths, along each ray path, so each line of X-rays through to a detector pixel is called a ray path. It's going to encode the information in all of those squares through the object into one detector channel. So I'm losing a dimensionality of my data. So I'm going from 2D, a two-dimensional grid of structure of a patient, and that's each line through that is going to be encoded as a single number in a detector channel. Now, as I said before, when I only go through a small amount of material, as is shown here, the blue arrow is only going through the small point, I get a small number registered as attenuation on my detector channel. When I go through a large amount of attenuating data, so here the X-rays are going through all of that long line of attenuating bone, I'll get a small detected intensity, but when I apply the Beer-Lambert law, it means it's a large value in terms of attenuation. So understanding what the detector pixels are measuring after I've applied the Beer-Lambert law, you can see the axes would be attenuation on the y-axis and then detector channel or position of detector channel along the x-axis. So, as we can see, the final part that I'm missing is I need to be able to undo that projection in order to get back to my three-dimensional visualization of the data. And the way I do that is by performing a reconstruction step. And we'll learn more about reconstruction in a later seminar. So, as you can see, we've gone full circle. We started by talking about 2D projection imaging. We've then discussed the simple form of the Beer-Lambert law, bearing in mind there's a lot more to come with the Beer-Lambert law as well, because we have to worry about more complicated material and energy scenarios. So we know that not all X-rays that come out of the source are the same energy, and so we have to account for that in a more complicated form of the Beer-Lambert law. And then we've explained how our discussion of volumetric data evolves from 2D projection to 3D projection data, and the fact that we need a reconstruction step. And that brings us to a close.